All right, now we're going to talk about something called conservation of momentum. Before we get into the specifics of conservation of momentum, I'd like to take a moment to just review what momentum is. So momentum is a variable that is a vector quantity, and it is calculated using the formula mass times velocity. So we have already learned that velocity is a vector, which means whatever direction the object is moving, we should have a positive or a negative value to that velocity to indicate the direction. Because momentum is the product of mass times velocity, the direction of the velocity is going to be the same as the direction of the momentum, which means that the momentum must also be expressed as a positive or negative. So objects that are moving forward, to the right, to the east, described as it being in the positive direction, those are all going to be positive values for our velocity. Therefore, the momentum of those objects will also be positive. Things that are moving backwards, so if I have an object that is moving to the right and something happens to it and now it bounces off to the left, well, that left, backwards, west, opposite direction would be a negative direction for my velocity, and so my momentum would correspond as a negative value as well. When we talk about conservation of momentum, conservation of anything means that the total amount available does not change. Okay, now you should have learned about conservation of various things in your previous science classes. So when we learn about conservation of mass, conservation of matter, we understand that once we've figured out how much mass or how much matter we have, that chemical reaction is going to take place and things are going to move around and we're going to end up with new stuff. But at the end of the entire reaction, all of the mass is accounted for. All of the matter is accounted for. It's the same idea here. When we talk about conservation of momentum, the total amount of momentum does not change. So now we are talking about two objects, each of them having their own amount of momentum. So we have object 1 and object 2. These two objects are going to have some sort of interaction, some sort of collision. And then after the collision, we're going to look to see how much momentum does object 1 have and how much momentum does object 2 have, but they're still going to have all of that momentum. Maybe object 1 lost some. Where did it go? It was transferred into object 2, right? Maybe object 2 had all of the momentum in the beginning, and then after the collision, object 1 has some and object 2 has some, right? So that's the main idea behind conservation of momentum. Once we know how much momentum is available, it does not change. So it says here the total momentum before is equal to the total momentum after. So what we see in this first line is our PI, momentum initial, is equal to our PF, momentum final. Okay, now I'm actually going to make this so I can write it a little bit more clearly. So let me give me some writing space. I just don't like how those font sizes did not transfer correctly, and I don't want there to be any confusion. Okay, so we say P initial equals P initial. I'm sorry, P final, sorry. So the total amount of initial momentum is the same as the total amount of final momentum. But we're going to have a collision, we're going to have contact between more than one object. In our class, we're going to keep it really simple. It's only going to be two objects. So I could write this line in more detail by saying that I have object 1 and object 2, and they each have some amount of momentum. The initial momentum of object 1 and the initial momentum of object 2 are going to be added together in order to tell me how much momentum I have total before the collision takes place. After the collision, I'm still going to have both objects accounted for. Nothing's going to disappear. So I still have object 1 and object 2. But now this side of the equation is going to represent the final amount of momentum for object 1 and the final amount of momentum for object 2. If I take those two values and add them together, they're going to equal my total momentum after. And what I should find that is that I get the same number on both sides. So if I have 25 kilogram meters per second of momentum before they collide, I will have 25 kilogram meters per second of momentum after they collide. Now, some of our questions are going to be this simple and straightforward. We're going to say the momentum of this object, momentum of that object. What's the momentum of object 2 after they collide? And we would plug it into this version of the equation. But most of the time, we are not going to be given the momentums. Instead, we're going to say we have object 1. This is the mass of object 1. Here's what object 1 is doing, and then there's a collision, and now here's what happens to object 1. Here is object 2, and here's the mass of object 2. Here is the speed of object 2 initially. After they collide, how fast is object 2 moving? Those are more along the lines of the questions we're going to get. So what do we do if they don't tell us what the momentum is, but they want to give us information in terms of mass and velocity? Very simple. We take it back to P equals mv, and we say object 1 has a momentum calculated using mass and velocity. So this would be mass of object 1, velocity of object 1, and this is the first object before they collide. Object 2 has a momentum, which is calculated by multiplying mass and velocity. So this would represent the mass of the second object multiplied by the velocity of the second object. And this side of the equation is where we would put the initial mass and velocity for our second object. Then the collision takes place. After they collide, object 1 is still accounted for. It has a mass and a velocity for object 1. But now this is going to represent the final velocity because this is after the collision has taken place. And so that is going to tell me the momentum for object 1 after the collision. Object 2 is still also present, and so it has a mass and velocity to determine its momentum. So this would be mass of object 2, velocity of object 2, specifically the final velocity after the collision. And we would then multiply those values to get their individual momentums and then add them together to get our total. So this last line is what we will be working with when we talk about our formulas for for collisions throughout the remainder of the notes. There are 3 main types of collisions that I want you to be familiar with. And again, these 1s and 2s should be subscripts, okay? So please don't get confused by that. Inelastic collisions are collisions where we have 2 objects that are going to collide. They're going to run into each other, and then they are going to stick together. You will be expected to read a description of a collision and tell me whether it is elastic or inelastic. So inelastic is sticky. They stick together. When we look at this equation, this tells me that I have object number 1, and so there's going to be a mass and velocity for object 1. I have object number 2, and so there's a mass and a velocity of object 2. These 2 objects are individually going to give me momentums, but I will add them together in order to determine how much momentum is available for this entire system. After they collide, objects 1 and 2 are now going to be stuck together. So if you look at the equation, I have M1 plus M2 in a parentheses. I am grouping the 2 masses because they are literally joining together to make one more massive object. So if object 1 was 5 kilograms and object 2 was 2 kilograms, then when they stick together, it would be a total of 7, right? Notice that in this particular equation, I only have one velocity. This is one object that is moving with a single speed, a single velocity. As it sticks together, it now becomes one object with one speed. And so that's why the equation only has one velocity. So this would be your VF on the right. Those would be VIs on the left. The next type of collision is called elastic. Elastic collisions are collisions where objects are going to collide. but then they are going to remain separate. So when we talk about identifying things as being elastic or inelastic, students often make an incorrect assumption, and they think that the objects have to be moving away from each other in order for it to be elastic. There is nothing in this definition that says anything about direction. It just simply says that they are separated. Okay, so they're not stuck together. That's the only thing you need to know to identify this as elastic. So what this means is that we have an object 1 with some momentum, an object 2 with some momentum, and those two objects are going to tell us how much momentum we have in total for this collision. Then the collision takes place, and if you notice, there is object 1 completely separate from object 2. So I'm going to have to calculate how much momentum for 1, how much momentum for 2, and then add those two momentums together to get my final momentum, okay? So once again, the left side of the equation is your initial. So this would be m1 v1 initial velocity, m1 v2 initial velocity, and then on the right-hand side, m1 v1 final velocity, m2 v2 final velocity, okay? All right, the last type of collision that we have is called recoil or explosion. We talked about what recoil was when we worked through some practice problems. We talked about kickback, and it's the idea that we have two objects that are going to experience a force that causes these objects to be accelerated in opposite directions. So in class, we talked about examples of a gun firing a bullet. We talked about a golf ball being struck by a golf club. And we said that there is a force that is going to be applied onto the golf ball because of the club. And because they are in contact with each other, the golf ball is going to apply a force back so that the golf club receives a force as well. Now, these two forces are supposed to be equal in magnitude. My picture's a little off, sorry. They should be equal in magnitude, but opposite in direction. So please look very carefully at a couple of really important things for this particular type of situation. For these recoil explosion questions, we are telling you that, first of all, this is an application of Newton's third law. Okay, we are saying that impulse and change in momentum are the same, and this is what we discussed with previous questions. We said that we had a force being applied onto each object, which was the same magnitude, and they are in contact for the same amount of time. And so there is my formula for impulse. So impulse is Ft. It is the same Ft for both, so the impulses are the same. Remember, impulse means change in momentum, so the change in momentums are the same. It says here that they're going to have the same initial and final momentums, but in opposite direction. And then it says that the total momentum for this type of collision is 0. So I'm going to talk about those last two bullets kind of together. It says that we have a total momentum of 0, but these objects are going to be put into motion in the opposite direction. They're going to have momentums with some velocity, but in the opposite direction. How is that possible? This is possible because we are going to have both of these objects initially at rest, and then this force is going to cause the object to have some value after the collision in the positive direction. And this force or impulse is going to have this object get some value in the negative direction. And so that is going to allow us to have a total momentum of 0. If we were to take these two variables, I'm going to write that a little bit bigger so we can see what I put. If we were to take these two variables and add them together, let's say that the impulse was 2.5 Newton seconds. That means that this object, the golf club, had an initial momentum of 0 because velocity was 0, and it changed by 2.5. So it's going to have a new momentum of 2.5, but in the negative direction. If the golf ball experienced an impulse of 2.5, because remember the impulse is the same in this case, it also had an initial momentum of 0. So since it changed by a value of 2.5, it's going to have a new momentum of 2.5, but it is moving in the positive direction. So if we were to find the total momentum of our two objects, we would take momentum 1 and momentum 2 and add them together. So it would be negative 2.5 plus a positive 2.5, which would indeed give me 0 as my total momentum, not because the objects aren't moving, but because the objects are moving with equal magnitude in opposite direction. So it says that for recoil or explosion collisions, our total momentum is 0. And the reason for that is because one moves in the positive direction and one moves in the negative direction. Now, I will have a separate video where I walk you through examples, word problems with numbers, and perform all the calculations to show you how each of these problems would be worked. But I want to skip ahead and I want to get to the end to explain how we get this formula right here. This is our equation that we can use when we recognize that we have a recoil or explosion type of question. What this is going to show us is that we have magnitudes that are the same, but they are in opposite directions. This is a negative m1v1, and this would be the final momentum, just to clarify, and that's going to be equal to a positive m2 v2, so this is where the momentum for the second object belongs, and this is also the final velocity for that object. Because they are equal in magnitude but opposite in direction, we end up with the momentum of one object after the collision, or after the explosion, however you want to say it, equals the momentum of the other object after the explosion or after the collision. One is positive and one is negative. So you can jump straight to this recoil explosion equation if you would like, once you realize that we have a collision type of situation. Again, this is a unique situation with a total momentum of 0.